Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of this course on robust control. So in the previous lecture we have seen this definition of a positive definite or semi-definite matrix, and we've also seen that there is a way to check whether given a square Hermitian matrix, that particular matrix is positive definite or semi-definite or not. And the way around is to check for the eigenvalues. We already know that the eigenvalues will be real, and therefore it makes sense to talk about the sign definiteness of real numbers and therefore those of the eigenvalues. And it turns out that a matrix being positive definite is exactly the same as that particular matrix having all its eigenvalues, the real ones, that is, because the eigenvalues, as I said, will be real, positive, strictly positive. All right. So we've seen the equivalence of these two conditions, the necessity and the sufficiency of this condition on eigenvalues for a matrix to be called positive definite. So in today's lecture we shall start by seeing certain, not necessarily offshoots, but certain properties of positive definite matrices. Okay. So here goes. So the first property that we shall see here is that suppose, so when I talk about positive definite matrices, you have to always assume that these matrices are indeed Hermitian matrices, that is, they come from Hn, right? That is the vector space we have defined for Hermitian matrices, right? So if, for example, you have a matrix Q which is positive definite, and again, as I said, what is implicit here is that this Q actually belongs to Hn. Okay? So I will not be mentioning this every now and then, but you should understand it from the context that whenever we are assigning this sign, right, this greater than, equal to, greater than, or less than, equal to, or less than, whenever we are using these signs are only admissible in the context of matrices or their sign definiteness if we have Hermitian matrices, otherwise it makes no sense. All right. Okay. So now suppose you have this Q and you have any arbitrary matrix of size m cross n, or rather n cross m maybe, yeah, because this is n cross n, that is the way we have defined. So let this be n cross m. Okay. So we are not imposing any special structure or special property on this matrix A. The only thing we are saying is that Q is positive definite, right. Then it turns out that we can actually say that the following matrix, that is A Hermitian Q A, is also going to be positive semi-definite. All right. Additionally, if in addition we have the kernel of this arbitrary matrix we have chosen to be the trivial subspace, that is a zero subspace, then we can get rid of this relaxed inequality, yeah, and we can make it a strict inequality, that is, then this A Hermitian QA is a positive definite matrix rather than a semi-definite matrix. Okay. Again, since I am not going into a formal proof, lemma, theorem kind of structure, I will also deal with this in an informal fashion. So I will just write it down, not explicitly as you would write a particular proof, but hopefully the way I write it will be convincing enough. So how are we going to claim this and why do we claim this? So suppose we choose an arbitrary x in C to the n, right. Then the question is, what about x Hermitian A Hermitian Q A times x, because this is the matrix whose definiteness we are about to check. So, if we can answer this and say that, well, irrespective of whatever this is always going to be, strictly greater than 0, then we will be done. So, now look, we observe that we can write this as x Hermitian A Hermitian. Observe that this is nothing but Q A x, and now let this A x be replaced by another y, right. Yeah. Okay. So, let me see what size I have chosen. Yeah, this is n cross m. Okay. So, x will probably be of size m, right. Yeah, because A Hermitian Q A is an m cross m matrix, right. Yeah, sorry about that. So, that is a correction you have to make. But on the other hand, this y, this is now of size n, right. This comes from C to the n, an n tuple of complex numbers, right. So, what we then have is, this is equal to y Hermitian Q y. Now, this is in general greater than or equal to 0 for all y.
So, just a small little clarification there. Actually, strictly speaking, this shouldn't be for all y. After all, if you are checking for all possible y that is not 0, then y Hermitian Q y is always going to be strictly positive. What we are actually checking for is for all x, remember, because we are hitting this object A Hermitian Q A with x Hermitian from the left and x on the right, right. So, this is actually for all x. That should be the notion, that should be the sense in which you should read this, and not for all y, so to say, right. So, I hope that sort of clarifies any misconception that this might have resulted in.
Now, note that we are bringing in this relaxed criteria. We are not calling this a strict inequality. Why? Because it may so happen that for your choice of x, y can turn out to be 0, right. Unlike in the definition of positive definite matrices, where we said that for any non-zero vector, right, for any non-zero vector, notice very carefully, for any non-zero vector, x Hermitian Q x must be positive. Okay. So, here also for any non-zero vector x, x Hermitian A Hermitian Q A times x. So, I can replace this x A Hermitian Q A by some other matrix, let us say some p, right. So, what I am going to check for now is whether this x Hermitian p x. Now, note that you can have non-zero x such that y is equal to 0. When can that be possible? Suppose A x is equal to y is equal to 0. That means x belongs to the kernel of A. Now, unless the kernel of A is trivial, that is A has full rank, right, full column rank, unless the kernel of A is trivial, I can always cook up some x such that Ax is equal to 0, where x is not equal to 0, and therefore, that particular non-trivial x will take my x transpose or x Hermitian p x to 0. So, therefore, I cannot guarantee that the moment you choose some non-trivial vector x, you will always get x Hermitian p x to be positive strictly. It can also result in 0. So, therefore, you can only go as far as the claim of semi-definiteness. If on the other hand, I am also told that if, however, the kernel of A is trivial, then the only way I can get Ax is equal to 0 is to have x is equal to 0. So, I cannot have a non-trivial vector x which takes my x Hermitian Px to 0. In other words, P will then be positive definite, and therefore we have this refinement, right. So in general, if A is not a full column rank, if the kernel of A is non-trivial, right, then you can only claim as far as positive semi-definiteness for this matrix, alright. On the other hand, if the kernel is trivial, then you can get rid of the relaxation and you can call it a strict inequality, and then you have positive definiteness instead of semi-definiteness, okay. So again, if you want to write it down as a formal proof, just whatever I have said, translate it into formal language and write it in a proper proof structure. But again, the purpose of this course is not to delve into matrix theory, but to give you an idea about why these results are true. Yeah, our goals are somewhat different. We will be harnessing these results later on to arrive at different conclusions, okay. So I will not really get into the formalism of writing a lemma and a proof, theorem and a proof and so on and so forth, okay. So that is the first consequence that we have seen of, or first property that we have seen of positive definite matrices, okay. So you take a positive definite matrix, take any other arbitrary matrix and take that arbitrary matrix Hermitian times the positive definite matrix times the arbitrary matrix, and that will be at least positive semi-definite, if not positive definite, and it can be positive definite if that arbitrary matrix has full column rank, right. So that is the first point that we have seen now. Let us look at the next property. Suppose you have a matrix Q which is positive definite, let us say Q1, and you have another matrix Q2 which is also positive definite, alright. And suppose you have two scalars, mu1 which is greater than 0 and mu2 which is greater than or equal to 0. Then we can say that mu1 Q1 plus mu2 Q2 is going to be positive definite, okay. And rest assured, if you flip these signs, that is if you say that mu1 is greater than or equal to 0 and mu2 is greater than 0, so you need at least one of these mu's, these scalars, to be strictly positive. The other one can be, you know, non-negative. Flip the roles of mu1 and mu2, it does not matter, right, it is one and the same. So just without loss of generality, I have chosen mu1 to be the strictly positive entity, yeah, and mu2 to be the non-negative entity. You can flip the roles. Why is this going to be true? You see, you take any vector, yeah, you take any vector and you take these terms individually. So you take x Hermitian Q1 x, take this to be one quantity, you take x Hermitian Q2 x, take these two quantities, you know that both of these are individually going to be greater than 0. Now when you multiply them respectively by these scalars that are positive themselves, yeah. So if mu1 is positive, then this is strictly greater than 0. If mu2 is non-negative, then this is greater than or equal to 0. But you have the sum now of a strictly positive entity and a semi-definite, or I am sorry, a non-negative entity. So their sum must be greater than or equal to 0. So the net resultant must be greater than 0. Yeah, so it's pretty straightforward to see. Okay, so that's a second consequence. I mean, we don't even need to write any formal proof of that sort. This is quite obvious, really. Just about addition, simple properties of addition of two scalars. That's all you need to know. Okay, what about the third property? Suppose you have Q as a positive definite matrix, then you will also have that Q inverse also a positive definite matrix. Why so? Now look, we have already seen that if Q is a positive definite matrix, then we can write this as x Hermitian lambda x, where lambda is a diagonal matrix with positive entries in the diagonal. Not just that, we also know what those positive entries are. They also happen to be the eigenvalues of this matrix Q. Right? We have seen this in the previous lecture. So now consider x Hermitian lambda inverse x. So what is this lambda going to look like? This lambda looks like, let us say, some lambda 1, lambda 2, these are all real numbers till lambda n. So this lambda inverse is then of course 1 by lambda 1, 1 by lambda 2, so on till 1 by lambda n, and all of these exist because they are strictly positive. So, you will not encounter this 1 by 0 scenario because none of these eigenvalues are 0, right. That is one condition. We have seen it to be an if and only if condition for positive definiteness, that all eigenvalues must be strictly positive, right. So, now if you take this to be the case, right, then q times x star this lambda inverse x is going to be what? X star lambda x x star. So, this much is q, yeah, this is q, and this is of course inheriting from here. Right. So, now you get rid of these braces and you get what you have here is this x and x Hermitian, this gives you identity. So, what you end up with is x star lambda lambda inverse x. So, again this pulverizes and gives you identity. So, in the next step you have x star x, right, and since these are unitary matrices, these x's x and x star, the x Hermitian that is, so this gives you identity. So, therefore, this is definitely equal to q inverse. If this is equal to q inverse, then what are its eigenvalues? Its eigenvalues are exactly 1 by lambda 1, 1 by lambda 2 and so on and so forth, right. And therefore, for a symmetric matrix, if all its eigenvalues are positive, because if lambda is positive, then 1 by lambda is also positive, right. So, therefore, all its eigenvalues are positive, which is again an if and only if condition for positive definiteness. So, if a matrix is positive definite, yeah, then its inverse is also going to be positive definite, okay. And we have just seen that. Okay. Now, is there any other interesting property that we can draw from this? Okay. So, let us see. Now, suppose we have positive semi-definite matrix. Suppose Q is now positive semi-definite. So, you are allowing for some of the eigenvalues to be 0. Yeah. What semi-definiteness in terms of eigenvalues implies is that all the eigenvalues of the matrix are at least 0, but not negative. Yeah. Of course, Q belongs to Hn, that is, it is a Hermitian matrix. Otherwise, again, as I said, this inequality and this sort of thing does not make any sense. Okay. All right. So, now then I am claiming that the rank of Q can be easily obtained. How? So, this is where again I am going to use this idea, this is exactly equal to the number of positive eigenvalues of Q. Okay. Why can we claim that? So, what is the rank? The rank is, remember, so let me complete this. Suppose Q is positive semi-definite, then we have that the rank of Q is given by the number of positive eigenvalues of Q. So, what is this rank? We know that the rank of Q is exactly equal to the dimension of the image of Q. Okay. So, where does Q take its inputs from and where does it map? It takes inputs from Cn, n tuples of complex numbers, and maps to another n tuple of complex numbers, right. So, we wondered that what could possibly be a vector. So, consider a vector in Cn, say V, all right. Now, again note that the columns of x star, what is this x? Remember, Q is equal to, always we are going to write this as x star lambda x. Okay. So, note that the columns of x star form an orthonormal basis for C to the n. If X is an orthonormal matrix, then X Hermitian X is equal to X, X Hermitian is equal to I. So, therefore, not just the columns of X are orthonormal, but the rows of x are also orthonormal. In other words, if you take the complex conjugate or if you take the Hermitian operation on the matrix, yeah, the transpose of the complex conjugate of the matrix, right, then also you will get another set of orthonormal vectors, yeah, and orthonormal set of vectors is always going to be linearly independent, as we have seen earlier. So, they form a basis for Cn. So, suppose x star, like we did the other day, can be written as x1, x2 dot 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 till xn, right. These are all vectors in Cn, sorry, these are all vectors in Cn, right. So, therefore, V can be written as a linear combination of these vectors, this vectors in the basis. So, V can be written as C1 x1 plus C2 x2 plus dot 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 till Cn xn, right, yeah. Now, if we try to map this, yeah, what do we get? We get that Q times V is going to be what? X star times this lambda times this x times what we have is x1 dot 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 till xn times C1 C2 till Cn, right. I urge you to check that this is indeed true. Why is this true? I am just writing this V. This V can be written in this form, right. This expression is tantamount to this, right, C1 times x1 plus C2 times x2 plus dot 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 till Cn times xn, right. But what is this? This is after all nothing but x star, right. So, what we have then is x star lambda x x star times the C1 C2 dot 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 till Cn. But this we know reduces to identity. So, what we then have is this x star times this lambda 1 lambda 2 dot 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 till some lambda r, let us say. Okay. So, we assume that suppose Q has R non-zero eigenvalues, okay. And here also another thing we are assuming is that the way we have written these columns of x, yeah, the way we have written down these eigenvectors corresponding to the non-zero eigenvalues, so that all the non-zero eigenvalues appeared in this order in the first R entries and the last n minus R happen to be the 0 eigenvalues. We can always do this permutation, right, depending on how we are writing this order of this x1, x2 and so on, right. Okay. So, now once we have this, then we have C1, C2 dot 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 till Cn. Now, what happens? This implies, again I am going to break this down and I am going to write this as x1, x2 dot 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 till xn times lambda 1, lambda 2 dot 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 till lambda r times the 0 and then the C1, C2 dot 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 till Cn, right. What does this entail? This essentially means that look, I have basically said that this means lambda 1 times x1, lambda 2 times x2 dot 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 till lambda r times xr, and the remaining all entries, these are going to be just 0 columns, no, because 0 gets multiplied with the remaining n minus r columns times C1, C2 dot 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 till Cn, right. So, this then becomes C1 lambda 1 x1 plus C2 lambda 2 x2 plus dot 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 till Cn Cr lambda r xr, all right. Yeah. So, what does this mean? What have we said? We have said that, well, we have taken an arbitrary vector v and we have seen that if anything belongs to the image of q, then it can be written in this form. So, any vector in image q belongs to span x1, x2 dot 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 till xr, right. The only thing that we need to now show is that any vector that belongs to this span also belongs to the image. But is that really so difficult? Yeah, it is not really that difficult, no. How do we go about this? Suppose you take any vector, yeah. So, any vector in image q is contained in this. So, the span is nothing but, if you write it in this fashion, the span is nothing but x1, x2 dot dot dot, this image of this particular matrix. It is just another way, no. The span of a certain set of vectors which are n tuples is basically like saying that it is in the image of a particular matrix whose columns are basically those n tuples, yeah, because this vector space and this vector space, I urge you to convince yourself that they are one and the same, yeah. So, that means that the image of q is contained in the image of this x1, x2 dot 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 till xr, yeah. Now, if we can show that the image of x1 through xr, this particular matrix, is also contained in the image of q, then we will be done showing that both are one and the same vector space. And what is the benefit of showing that they are both one and the same vector space? We know exactly that the dimension of the image of x1, x2 dot 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 till xr is equal to r. We know this. Why? Because of course, the columns of the matrix x star are linearly independent, they are orthonormal set of vectors, right. So, they are linearly independent. So, the dimension of this image is exactly r, right. So, all that we now need to show is that anything that belongs to this belongs to the image of q. So, suppose y belongs to the image of x1, x2 dot 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 till xr, this one, right. Therefore, y is equal to, let us say, let me use some other variable, alpha 1 x1 plus alpha 2 x2 plus dot 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 till alpha r xr, okay, right. So, therefore, I can safely write this one as y is equal to x1, x2 dot 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 till xr, xr plus 1 dot 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 till xn. Notice very carefully what I am doing here, and then I can write this as alpha 1, alpha 2 dot 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 till alpha r, and I keep the remaining fellows 0, right. And this then turns out to be nothing but x star times alpha 1, alpha 2 dot 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 till alpha r, and the remaining all zeros, right. Now, I have to show, now the question before me is, does there exist, what should I name this vector? Does there exist, say, some, okay, I am running out of variable names. W belonging to Cn such that Q times W is equal to Y. If so, then I would have proved that any time you pick a Y that belongs to the image of this, it also belongs to the image of Q, because that is the definition, no. When something belongs to the image of Q, it means that there exists some W such that Q times W, yeah, so Q acting on W maps to that particular vector. So, we are trying to solve for this question whether there exists QW should show that there exists W such that QW is equal to this Y, but this Y is what? Y is this X star and this alpha 1, alpha 2 dot 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 till alpha r and then all zeros, right. But what is this? This Q I can write as X Hermitian lambda X, yeah, times W is equal to some X star times alpha 1, alpha 2 dot 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 till alpha r and all zeros, right. So, then if I operate with X on the left on both sides, I will get this expression but now look, what is this? This is basically nothing but I have, if you look at this structure now, what did I call them? I hope I call them lambda 1 through lambda and lambda r, right? Yeah. So, lambda 1 through lambda r. So, this is lambda 1, lambda 2 dot 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 till lambda r and then the remaining all zeros. This is what this matrix is, right. And this x, I can write this x in this fashion, right. I can write this as x1 star, x2 star dot 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 till xn star times w is equal to this alpha 1, alpha 2 dot 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 till, sorry, you have some alpha r and then the remaining zeros, all right. In other words, what I then have is, if you perform this, carry out this multiplication here, you will get that this is equal to lambda 1 x1 star, lambda 2 x2 star dot 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 till lambda r x r star. These are of course row vectors, right, and the remaining rows they get multiplied with these zeros here, right, in this diagonal entry. So, this is 0 row of zeros like this, yeah, times some w, right, times some w is equal to alpha 1, alpha 2 dot 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 till alpha r and then this 0, yeah. So, can we show that there exists some solution for this w? Well, for starters, you might say that, well, what is the guarantee that there does exist some solution, yeah. What is the guarantee that there does exist some solution? So, for that you need to observe that how many equations are here? There are R equations, right, and these R equations they exactly match with this. So, all that you need to solve for is that basically lambda 1 x1 star w is equal to alpha 1, or rather you can divide it out by these lambda 1 x2 star w is equal to alpha 2 by lambda 2, and then you have x r star w is equal to alpha r by lambda r, yeah. So, how many parameters do you have to play around with? In W you have n parameters, right. So, you have n variables and you have fewer equations than that. So, what sort of a system is that? It is an underdetermined system, right. Not just that, you see that there is a perfect matching here, right. So, this x1 star, x2 star, xr star, these are all known to you. The only unknown to you is this w. The unknown here is this w, right. So, the question is, can we always find a w such that these R constraints can be met? And I am putting it to you again, go back to a bit of linear algebra and solving linear systems of equations, right. And you will find that you can always find a solution to this kind of an equation, yeah. There will always exist a solution for this. Why? The hint is, again, if you want to brush up with your linear algebra, the hint is that this is a set of R equations, and if you just look at this matrix x1 star, x2 star, dot 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 till xr star, if you just look at this particular matrix here, this is an R cross n matrix and its rank is equal to, so let me write the rank here, and its rank is equal to R, its full rank, right, full row rank. So, when you have an underdetermined system of equations where the matrix has full row rank, yeah, you can always find a solution. Whether the solution is unique or not, that is a different question. Yeah. So, you can have multiple different solutions, but my point was that whether there does exist some W, and that question is well and truly answered by a simple knowledge from linear algebra, that when you have this sort of a fat matrix with full row rank in a system of linear equations, you will always be able to find at least one solution for this system of equations. Okay. The question is not whether you can find the solution, the important question in such cases arises as to whether that solution is going to be unique or not, and if not, then what is the best solution. Okay. So, those of you who have actually tried to fit in curves, yeah, best straight line approximation, essentially, again you can go back to your lessons in linear algebra and you will see that it is essentially a question of what is the best fit curve. Yeah. So, there are different ways of interpreting this. If you go through a course on linear algebra, you will see that it is basically fitting something as best as you can with the least amount of error. Okay. Right. So, what is the best fit curve that you can get? So, you want to get some norm minimized maybe, yeah. So, you want to get that particular solution which has a minimum norm. So, out of all the W's that you can get, yeah, you can put in some additional constraint, because otherwise there is a plethora of solutions to this, right. The dual of this problem is when you have an overdetermined system of equations, you have more equations and lesser fewer variables, right. So, you may not have a solution that exists. So, then what is the best possible solution you can get? There will always be some error. It turns out then there is this orthogonal projection matrix that gives us some solution, right. You project it onto it, like you project the vector and you see when the error is perpendicular, yeah, orthogonal, then you have the best possible solution. So, again those are lessons in linear algebra, we will not get there, but the point I was trying to make is, let us go back and let us not lose sight of that. The point I am trying to make is that whenever y belongs to this image, it also belongs to the image of Q. So, therefore, if you believe me on this, if you do not believe me, just go back to your linear algebra lesson, but if you believe me on this, then we deduce that y belongs to the image of Q, and hence the image of x1, x2 dot 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 till xr is also contained in the image of Q. So, look at this deduction here and look at this deduction here, right. So, if a set A is contained in a set B and the set B is also in turn contained in the set A, then they must be equal, right. So, therefore, we have that the image of x1, x2 dot 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 till xr is equal to the image of Q, and therefore, the dimension of the image of Q is going to be R, which is equal to the number of non-zero, or rather number of positive, in this case positive eigenvalues of Q, which is a positive semi-definite matrix. Yeah. So, it turns out that the number of positive eigenvalues of a positive semi-definite matrix is also equal to its rank. Okay. So, the reason why I put in the effort to go through all this trouble is because we will be using, with a subtle modification of this result, we will be using this to prove a very big result, one of the biggest results in matrix theory, that is the singular value theorem, singular value decomposition, right. So, we will use, maybe not prove it, but some very interesting and nice properties of singular value decomposition we shall see follows immediately from whatever effort we have put in deriving this current result that you see before yourself. Okay. Okay. But before we get into singular value decomposition, there is a bit of work to be done still. So, let us define the square root. Now, you see, you are familiar with the square root of real numbers, maybe positive numbers when it leads to positive real numbers, when it leads to a real number, negative real numbers, it leads to complex numbers or imaginary numbers, right. Okay. So, the square root of a positive definite matrix, say Q is equal to x Hermitian lambda x is given by x Hermitian lambda to the power half times x. What is lambda to the power half? Where lambda is equal to this lambda 1, lambda 2 till lambda n, and lambda to the power half is then defined as square root of lambda 1, square root of lambda 2, all positive square roots. Yeah. Not just that, therefore, q half is equal to this is also positive definite. So, the square root of a positive definite matrix not only exists, but it is also in turn positive definite itself. Okay. Again, not very difficult to see, you can immediately see it follows straight away from here. If you want to just take it as an exercise, you can try to prove it, but really there is nothing much to prove, I put it to you, right. Okay. So, now having seen this, now we are in a position to introduce a new kind of a notation which at first might seem a little weird or off. So, suppose Q1 and Q2 belong to this Hn, that is, they are both Hermitian matrices. Then Q1 greater than Q2, yeah, these are matrices, right. This is a notation that we have not seen maybe anywhere so far in our standard courses. But now that you have understood, the notion of this positive definiteness, yeah, this begins to make sense. How? Then this actually implies, or it should be read in the following manner, that Q1 minus Q2 is positive definite. That is all that it means. When you say that one matrix is greater than or equal to another matrix, it means that you take the difference between those matrices, which is one operation you understand, element wise difference, yeah, then that matrix is either positive definite or positive semi definite. So, in that sense this should be read, not in any other sense. Okay. So, that is what this notation basically implies. Okay. So, with that we have mostly kind of defined all the important properties and definitions that are now required, and we shall be harnessing these quite often in our course, right. So, this is very important to understand what this inequality between two matrices implies, right. Once you are dealing with Hermitian matrices, all of this, even though weird at first sight, makes perfect sense, right. So, it makes sense to say that Q1 is greater than Q2. Just like you compare two numbers, you can actually even compare two matrices, but of course, it is not entry wise comparison. It is basically to say that the difference of those matrices had better be positive definite. So, let me just complete the picture. It means that for all x not equal to 0, x Hermitian Q1 minus Q2 times x is a scalar that is strictly positive. Okay. That is how this should be read. So, whenever you encounter this, immediately it should flash before your eyes that this is what it implies. Yeah. Be under no other misconception. All right. So, now we will see another very important result which is harnessed again, which is used on and off, which is basically the so called Schur complementation or Schur complement formula. It is a very useful result, and if you read, I mean hopefully after you have completed this course, if you read some literature or read some journals that harness some tools or techniques from robust control and using LMIs, etc., you will invariably at some point in time encounter the Schur complement formula. So, what is the Schur complement formula? It says that the following two claims are equivalent. Okay. So, suppose you have, suppose Q is greater than 0, yeah, and M minus R Q inverse R is greater than 0 for Q and M belonging to the vector space of Hermitian matrices, and of course R has no such restriction, R could be any arbitrary matrix. Okay. So, R could be any arbitrary matrix, R has no such restriction. Okay. So, we are only, remember this, we are only imposing this restriction of being Hermitian on Q and M. Okay. Yeah. So, this condition, then 2, okay, what is 2? 2 says that the following matrix is also positive definite. Okay, and vice versa. So, this is an if and only if condition. Okay. These two results are equivalent. So, of course, let me pull out, let me okay, let me erase that suppose, it gives a, yeah, now we have it. So, now if you are given, so let me erase this if and then as well, yeah, because these are after all equivalent conditions, no, so I should not write it in the if then fashion. So, if I tell you condition 1, that is Q is positive definite and M minus R Q inverse R is also positive definite when Q and M are Hermitian matrices, right, then it is the same as in this packed notation. If you pack up this big matrix M R Hermitian and Q in this manner that I have written here, and I claim that that is positive definite, it is one and the same, there is absolute equivalency between the two, there is no difference between the two. Okay. Why do we say that, and how do we go about proving this? So, here is what I will give again a brief sketch of the proof. I will again not go into the details of this proof. So, consider that we have let us say the first one, when we say Q greater than 0 and M minus R Q inverse R, okay, I think that is R Hermitian, no, yeah, probably it is going to be R Hermitian if I am not mistaken, yeah, otherwise it does not make sense, because R is not a symmetric matrix or a Hermitian matrix, right. So, the only way that this entire term is going to be also Hermitian, yeah, after all if you are saying it is positive definite, it has to be Hermitian. So, then this has to be R Hermitian. Okay. All right, good. So, now this is equivalent to saying that I can pack up this matrix and write it as Q and pad this with the 0 blocks and say R Q inverse R star is positive definite, right. Because after all, what is this? This means that for any appropriately chosen x of proper size, that is probably of n, right, if it is Hn. So, x Hermitian Qx is positive definite and y Hermitian, this big fellow, this M minus R Q inverse R Hermitian times y is also positive definite. Now, if you pad them together, so you have any x padded with any y and you hit it with this on the left and its transpose, that is this x Hermitian y Hermitian on the right, yeah, and this is also going to be positive. It is the same as packing up these two together in one single matrix form. So, this is true, right. Now, if we can show that this is tantamount to this, or that these two conditions are equivalent, then we are done, because we have already seen that this condition and this condition are equivalent. Whether I write it as two separate relations or I pack them up in a single matrix and write, it is the same. So, therefore, I can now say that, well, if I can now show the equivalence between this and this, then I will be done. But how do I get to this equivalence? So, consider that I R Q inverse 0 I times Q 0 0 M minus R Q inverse R Hermitian times I 0 Q inverse R Hermitian I. Look at this. What is this matrix? What does this remind us of? Call this some, or rather call this some A. Then this is basically a Hermitian, right? And just recall a while ago towards the beginning of this lecture, what have we seen? One of the important results about positive definite matrices. Yeah, we have already seen this result that if you have Q, which is a positive definite matrix, yeah, then you have this A Hermitian QA, yeah, it is going to be at least positive semi definite. And additionally, if this happens to be a matrix with a trivial kernel, yeah, then it is actually also going to be positive definite. Okay. So, all that we now need to show is that this, yeah, is going to be the same. Okay. We will see that later, but what about this? Does this actually boil down to something interesting, something that is of interest to us? Well, just perform this operation here. Okay, maybe we can actually flip the order, you know, the way I have written it here. Yeah, probably I should, it really matters not, right? It is M minus R Q inverse R star, and this is Q. I could have also flipped the order of this, but anyway, it doesn't matter, right? So, I can just switch the places between these two, so that this matrix that I have chosen just fits in, right? It really does not matter whether you take this as the 1 1 block and this as the 2 2 block, or you flip it over. Okay. Let us just check. Okay. So, what happens when you operate this? When you take the first two products of this and this, then you get I. So, you have M minus R Q inverse R star and 0 times this. In the second case, you have I times 0 and R Q inverse times Q. So, that is R, and this one you have 0 and 0. So, just check, this is block by block multiplication, it is the same as matrix multiplication, yeah, and this is Q times the final, which is final matrix, which is I 0 Q inverse R star I, all right. So, now you see that when I multiply this with the identity and then I add to it this, what gets subtracted is basically this R Q inverse R star. So, I am then left with only this M in the 1 1 block. In the second block, this gets multiplied with 0 and the R gets multiplied with I, so it leaves me with R. Yeah. Finally, when I multiply here 0 times I and Q times Q inverse R star, so that is just R star I am left with, R Hermitian. Okay. And lastly Q, yeah. So, what can I say about this? This is at least greater than or equal to 0, yeah, alright. But now, can I say that the A matrix has a kernel of only the trivial subspace, kernel comprising only the trivial subspace? So, look at the kernel of this A matrix. All right. What can we say about this? Let us write it down. So, it is I 0 Q inverse R Hermitian and I, and suppose you have x y, I am partitioning this in this fashion. So, this is going to be equal to x, yeah, and this is Q inverse R star x plus y. So, you see, if this has to be 0, then I must have that x is equal to 0 and q inverse r star x plus y is equal to 0. But in this expression, second expression, if I now plug in x is equal to 0 from the first expression, I am then left to conclude that y must be also equal to 0. So, in other words, if any matrix such as this belongs to the kernel of this matrix, then it has to be only the 0 matrix. So, therefore, the kernel of A is basically the trivial vector space, and therefore, I might as well drop this, yeah, and I might actually say that this is tantamount to saying that M R star Q is actually positive definite. Yeah. So, that is basically it. So, we have shown the one-to-one relation between this, shown that both of these relations are equivalent. So, it is a very important relation, Schur complementation formula or Schur complement formula that we shall be using very often. Before we conclude today's lecture, I would briefly like to at least introduce the main idea of singular value decomposition. We shall delve deeper into this topic in the next lecture. But this, I put it to you, is the single most important result probably from which you can derive most results in matrix theory. The moment you find that you are unable to prove some result, you better go for the singular value decomposition, and more often than not you see that the results then start to follow almost immediately. Okay. So, what does the singular value decomposition say? This holds for any arbitrary matrix, square or rectangular. Suppose A is a matrix that is of size m cross n, alright, and P is the smaller of the two numbers. So, it could be a square matrix, it could be a tall matrix, in which case m is greater than n and P is then equal to n, the number of columns, or it could be a fat or wide matrix, in which case there are more columns than rows, in which case P is going to be equal to m. Okay. Then we say that we can write then A is going to be equal to some u times some sigma times some v conjugate or v Hermitian rather, where u is of size m cross m. Yeah, actually we can say more. Yeah, so u is of size m cross m and u star is equal to u star u is equal to identity of size m. Okay. V is of size n cross n, where again, so these are unitary matrices, is equal to identity of size n, and sigma, yeah, sigma looks something like this. So, sigma can be described by is such that sigma IR, okay. So, the IRth entry, or rather let us say ijth entry, yeah, why bring in R, ijth entry is equal to 0 unless j is equal to I and there is this special ordering and sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma 3. Likewise, there is this ordering till we have sigma pp which is greater than or equal to 0. So, all of these are non-negative entries sitting on the IIth as the IIth entry of the sigma, and clearly this sigma belongs to size m cross n. Okay. So, this is a very important factorization, okay, and this will always exist for any matrix irrespective of whether it is a square matrix, whether it is a rectangular matrix, whatever the size you choose of this. Okay. So, there are some very nice and important consequences of this. Of course, you might see that for square Hermitian matrices, you have already seen what the singular value decomposition looks like, okay, where you have U is equal to V. Yeah. Of course, we have written it as X Hermitian lambda X, right. So, let X Hermitian be equal to U, yeah, and then V Hermitian is going to be equal to X, and sigma is then replaced by lambda, right. So, we have already seen that for Hermitian matrices that are positive definite, we have already seen what the singular value decomposition looks like, but that is not the primary goal of studying singular value decomposition. That seems like a very narrow objective, yeah, that is a very special case. I am claiming that singular value decomposition exists for every single matrix that you can conceivably conjure, okay. And we will see that this ordering is also at our disposal. Just like we can order these eigenvalues, actually we will see that these singular values, so these numbers are, by the way, also called singular values of A, okay. So, in the next lecture when we come back, we have already introduced what the singular value decomposition looks like. Again, if this is something you have already done, it might sound repetitive, but we will risk that at the cost of being repetitive. We will still see somewhat a sketch of the proof, which will convince you that the singular value decomposition exists for every matrix, yeah, and then we will see some beautiful properties, how we can extract certain important subspaces like the kernel and the image of a matrix just by looking at this singular value decomposition. And there again, the result we have taken so much pains to establish today a while back for symmetric matrices, for Hermitian matrices, will come in very handy, okay. So, till then, take care.